Here we are at the beginning of Chapter 5, the second semester of calculus. I hope you'll read along on page 263. It's well written. It gives a good overview of what we've learned, first semester calculus, what we're about to learn, second semester calculus, and how the two are related. So recall that we have been working on how to compute the derivative, which is a function that gives the slope of a tangent line to a function anywhere along that function. To find the derivative, to differentiate, gives the name, the common name for that first semester of calculus. It's commonly called differential calculus, the math of finding and then using derivatives. We learned along the way that if we didn't have an actual function to differentiate, we could approximate a derivative by finding the slope of the secant line, which is the same as f of b minus f of a over b minus a, the average rate of change of the function. So second semester starts with what you might think is a completely different problem. The founders of calculus, they were interested in finding the area under a curve. We'll talk in a second about why they wanted to do that. So it turns out that the notation we're going to use to indicate that we want to find the area under a certain curve is called the integral. So second semester calculus is commonly called integral calculus, as opposed to differential calculus, the calculus of finding derivatives. And so not only are we going to learn how to find the area under a curve and how to use this integral notation, we're going to start to learn about the connection, the surprising, we didn't really expect it, connection between finding derivatives and finding areas under curves. And another parallel we can draw is that one of the most important things we're going to learn isn't just how to find the area under a curve, which we will learn how to compute exactly, even for the craziest looking curves. You wouldn't think we could find the area under. But it's to approximate that area, the same way we learn to approximate the derivative by finding the slope of a secant line. So you know from geometry that if you have a picture, a geometric figure, you could chop it up into separate pieces, find those areas separately, and add them together to get the area of the whole. So we're going to do something similar. We want to find the area of a curve, the area under a curve. If we can't do it exactly, we will split up that area into smaller and smaller areas and find an approximation. So commonly we're going to use rectangles or trapezoids to fill in the area under curve so we can form an approximation. All right, so second semester calculus, why would we be interested necessarily to find the areas under curves? We know how to find lots of different kinds of areas because of our study of geometry. But to understand why we're so interested in finding the area under a curve, go to this problem that you've been doing for many, many years now. If a train is traveling at 75 miles an hour between 7 a.m. and 9 a.m., how far does the train get? What distance has the train traveled during those 2 hours? So we dig out this formula that we've used forever, which is rate times time equals distance. So if the train is traveling 75 miles an hour and it travels for 2 hours, we get that the train travels 150 miles. And notice that the units work out. The units on the rate are miles per hour, and the units on the time is hours. So the hours cancel out, and we get miles as the units of our final answer. So check out what our friends who were developing calculus started to think about. If you look at the graph at the bottom left, this is page 263 from your book. If I graph the velocity 75 miles per hour and I mark 7 a.m. and 9 a.m. so that my time axis is measured in hours, the math I'm going to do, I'm going to multiply 75 times 2. Notice that happens to give the area under this curve, so the shaded blue region in the bottom left graph. So here's the problem. Cars, planes, particles, people, planets don't travel at a constant velocity. So this problem that we've been doing, rate times time equals distance, for forever, and which you did in your little warm-up homework assignment for last night, it's good, but it's kind of a farce. We don't move like that. So how could we compute distance traveled, acknowledging that most of the time velocity changes? Most of the time velocity is not constant. So the founders of calculus started to wonder, if you look at the bottom right corner, the graph there shows a velocity function that is not a constant. So the question is, does the distance traveled still match up with the area under that curve? And it turns out they did a lot of work to prove it, but it turns out that yes, the distance under the velocity curve gives distance, the area under velocity curve gives distance traveled. And that is your number one most important fact for maybe all of second semester calculus. As long as velocity is positive, the area under the velocity curve gives distance traveled. So here's what we're going to practice. We're going to practice computing distance traveled by finding the area under the velocity curve when velocity is not a constant function. So take a look at this first problem. A car moves with velocity 3/5 t plus 4. That's measured in miles per minute, and the car is going to travel for 5 minutes, starting at time 0 and ending at time 5. The question is, how far does the car travel during that time? So it might seem scary because I just said we're going to spend our whole second semester of calculus computing areas under curves. How am I going to do this, before I even learned anything? But notice if I graph this velocity curve, which is v of t is 3/5 t plus 4. I'm going to start with a y-intercept of 4. I notice that my velocity curve is linear. And I could compute, that's 5, which is 3 plus 4 is 7. And what I'm looking for is the area under the velocity curve from time t equals 0 to time t equals 5. So I want to find the area of that pink trapezoid I just colored in. That's going to give me distance traveled. This works because in this one case, and in a few cases we'll see, I can name the area described. It's a trapezoid, and I learned in geometry how to find the area of a trapezoid. So that's what I'm going to do here. Notice that units on time are minutes, and units on velocity are miles per minute. So I'm going to be multiplying essentially miles per minute times minute. I'm going to get miles as my units on my answer. So here we have a trapezoid. How do you find the area of a trapezoid? Well, just remember that a trapezoid is a quadrilateral with two parallel sides. So see these two parallel sides? What we do is we find the average of those sides. So this side over here has a distance of 4. This one has a length of 7. I'm going to find the average. That means I'm going to add those two together and divide by 2. So it's the average of we call them the bases, although notice that in geometry you probably had your parallel sides were horizontal. Here our parallel sides happen to be vertical. And then I'm going to multiply by the distance across the other dimension. So in this case, it feels like the width of the trapezoid. This is 5. So that's 4 plus 7 over 2, which is 11 halves times 5. The area under the velocity curve is 55 halves, which gives me my answer to the original question, which is, what is the distance traveled? The distance traveled is 55 halves. Miles per minute times minutes gives miles as the units. So this another one we can do. This is the second one. A particle travels with a velocity. Again, I've been given a velocity function. And as long as when I graph the velocity function and look between time 0 and time 4, if I get a geometry shape that I recognize, whose area I can find, I'm going to be able to answer this question. Well, I hope you'll start to recognize this. If I said x squared plus y squared equals 16, I hope you'd start to recognize that or remember that that's a formula, that's not a function, but a curve that describes a circle whose center is the origin and whose radius is 16. Sorry, whose radius is 4. Notice if I tried to isolate y, I'd get y equals the positive or negative square root of 16 minus x squared. So the velocity function I've been given here, it's just the positive square root of trying to solve the equation for a circle for y. So this is been asked to find essentially the area of this quarter circle, pretend that's a quarter of a circle. Really, there's a semicircle up here that starts from -4 and goes to 4. And I want to find the area of this quarter circle because look, my time only goes from 0 to 4. So what's the formula for the area of a quarter circle? That would be 1/4 pi r squared. So in this case, pi times 4 squared, which is 16 pi divided by 4, which is 4 pi. So if the velocity is measured in centimeters per second and time is measured in seconds, then our distance traveled is going to be 4 pi centimeters. So just one more, it would be very common for you to have a problem like this on the AP test. This one came from an AP test. If I've been given a graph of the velocity of a car, I can tell here velocity is positive. The question is, how far does the car travel during the interval 0 to 24 seconds? Give units with my answer, and I've been told that velocity is measured in meters per second, time is measured in seconds. So my units on my final answer are going to be meters per second times seconds. The seconds cancel out. I'm going to have meters as the unit, and that makes sense because I've been asked about distance traveled. Distance traveled can be measured in meters. So how do I find that distance traveled? I'm going to find the area of this trapezoid. This time our trapezoid is geometry style with our parallel sides are horizontal. Remember, I'm going to find the average of the parallel sides, which in this case, the length of the top is the difference between 4 and 16, so that's 12. The distance across the bottom, that goes from 0 to 24, so 24. I'm going to find the average of those. I'm going to multiply by the other dimension. In this case, we could think of it as the height. So those 2 points there, they have a y-coordinate of 20. The height of this trapezoid is 20. So I get 12 plus 24 times, these guys can cancel out to leave me 10. So that's 36 times 10, 360 meters is the answer.